In the previous video, we saw that if you take the basic non-inverting amplifier to the absurd extreme of making the feedback resistor infinite or removing it altogether, then it became a device that we called a comparator, because basically it compares the input voltage to ground, and the output then takes on the maximum value of whichever sign is appropriate. If the input is negative, the output goes to minus power supply level. If the input is positive, the output goes to the positive power supply level. If we simply reverse the two inputs and ground the non-inverting input and put our input signal on the inverting input, then this becomes an inverting comparator, because remember, your op-amp basically is a differential amplifier. It looks at the difference between the two, and you just flipped the sense of where the minus sign is, so now it takes ground and subtracts the input voltage VI, so the differential input is negative VI, then it just amplifies the heck out of it, and so now you get an inverting comparator, and the I/O characteristic curve looks like this. It's just flipped over relative to the non-inverting comparator. Now that's pretty simple, and that can be useful. It depends on what you want to do. Next thing we can do is we can put our input on the non-inverting input like we did with the standard non-inverting comparator, but now instead of putting ground on the inverting input, we can put some other voltage there. We'll call that V sub R. If the difference V sub I minus V sub R is positive, then the op-amp just amplifies the heck out of it and the output goes to the positive supply rail. If, on the other hand, VI minus VR is negative, the output of the op-amp goes to the negative supply rail. So now we have something that compares our input to some voltage. It doesn't have to be 0 volts. It can be whatever we put on V sub R. With most op-amps, you generally don't want to exceed the power supply levels directly connected to the inputs, so typically you would not want to make V sub R or V sub I go beyond plus or minus 15 volts, but there are ways to deal with that if you really need to exceed those levels, but not a good idea to directly connect those to the input. So now your I/O characteristic curve looks like this. If your reference voltage, V sub R, is positive, then that transition point is going to be at that positive value of V sub R. If it's negative, it'll be negative. You can do the same thing with this circuit that you did with the really basic non-inverting comparator that compared against ground by flipping the sense of the two inputs, and you can make your reference voltage V sub R be on the non-inverting input and your input V sub I on the inverting, and now you have an inverting version of that variable compare voltage comparator. If, for example, V sub R was positive, your transition point would still be over there on the positive side of 0, but if V sub I is greater than V sub R, the output would be high, and vice versa. And of course, if V sub R was negative, then that transition point would be to the left of the vertical axis. Now that was a really quick introduction to the basic flavors of the comparator. You've got the simple non-inverting comparator that compares against 0, you've got the inverting comparator that compares against 0, and you've got both an inverting and non-inverting version of a comparator that compares the input to some voltage, whatever it happens to be. With all of these circuits we have looked at, there is a problem. Depending on your application, this can be a very serious problem. In some cases, it doesn't matter, you can get by with just the simple basic comparator. In other cases, you will have a disaster if you don't take care of this problem. We will present that problem in the next video.